Hi guys, and welcome to another video pre-calculus lesson. Today we're going to cover lesson 11, where we're going to talk about how to graph, factor, and do a little bit of a review for exponents. We've talked about linear functions before. Linear functions make straight lines. Yes, the root word of linear is line. And but so far we've only talked about slope-intercept form, where if you have the slope and the y-intercept, you can graph it. Today we're going to talk about something called point-slope form, where if you have a point and a slope, then you can go ahead and graph. Now, this is our point-slope form. Y minus y1 is equal to m times x minus x1, where if you have any point, x1 and y1, you can plug those in, and any slope, you can plug them in. We can figure out the point and the slope for our equation. First thing we're going to do is we're going to look at a few examples that have equations written in point-slope form, and we want to try to figure out, well, what is the point from the equation and what is the slope of that same equation. So I'm going to go ahead and rewrite this equation. Y minus y1 is equal to m times x minus x1 over our equation. We're going to see what lines up. And what we want to do is we want to figure out, well, what is the point, which is going to be in the form of x1, y1, and what is the slope, which is going to be m. Now, looking at this equation, I can see that x1 lines up over the 2, and the y1 lines up over the 3. But if we look at the original equation, both original equations both start with negative signs in front of x1 and y1. That means that whenever we try to find the point, it's always going to be the opposite sign of our term. Like in this case, we would end up with our x1 being 2 and our y1 negative 2 and our y1 being 3, because in our original equation it's negative x1, and this would be the same thing as like minus negative 2. So in this case, x1 is negative 2. And y1 is going to be 3 because the original equation was already negative, so y1 is just going to stay at 3. Our slope is always going to be the number in front of our x value. So in this case, our slope is 2. So I'm going to practice this a few more times. So basically, we're reading the information that they give us, and we're trying to figure out our point and our slope. Let's try this again. If we know that y minus y1 is equal to m times x minus x1, our point and our slope would be as follows. Our point is going to line up with our x1. In this case, is going to be positive 4. And our y1 is going to line up with our 8, and it's going to be negative 8. Our original equation is minus y1, and because it's positive 8, we're going to have to use the opposite sign. The slope is going to be the number in front of the x, and we're going to go ahead and say it's 1/2. So this would be our point and our slope. It's just lovely that we have the fire truck or whatever it is going off in the background. The big debate right now is, do I close the door to make it a little bit worse, or make it a little bit easier to hear, or do I just like not do anything? Let's close the door. I don't even know if they can even hear this on the recording. Close the door and it got louder somehow. Or the window. Oh, that's better. Okay, let's try this last one. Thank you for hanging in there, class. We have y minus y1 is equal to m parentheses x minus x1. And what's different about this problem is there is no parenthesis. This is actually not lining up exactly. The y and the minus y1 lines up, but it's a little bit different. What we see here is that there's no parenthesis, And the way that we can make this line up is if we factor. If we look at the right half of this equation, we notice that there's a GCF of 2 for each of these terms. So I could factor out a 2 in front, and I get x plus 3 is all equal to y minus y1. And now the form does line up and match a little bit better. So we can pick our point. Our x1 is going to be -3, and our y1 is going to be +1, and our slope is going to be the number in front of the x. We're going to say our slope is 2. All of this is going to lead us to our next set of questions into how to actually graph using point-slope form. Now, if you wanted to, you could distribute the slope with the x plus x1, and you could rearrange this so you have slope-intercept form. But we want to practice finding the point in the slope, because this is something that calculus classes will do when you have to find find the slope and draw a tangent line of a curve at any particular point. They use point slope form, so that's why we're kind of going over this today. So let's do the same thing we have been doing. We need to find a point and a slope, and then we're going to try to graph this. If we know that y minus y1 is equal to m times x minus x1, we know that our x1 is going to be -1, opposite sign of +1, and our y1 is going to be 4. Our slope is going to be 3/2, and if we graph this, we're just going to graph our point and our slope. -1, +4 is about right here, -1, +4. And then from this point, we're going to have a rise over run of 3/2. So from our point on the graph, we're going to rise 1, 2, 3, and run 1, 2. Rise 1, 2, 3, run 2. And we're going to end up with a line that looks something like this. Now, one thing I do want to kind of point out, for problems like this, if the slope is positive, from left to right, our graph should be going uphill. And that's going to be a positive graph. Number one mistake people make at this point when you're graphing lines like this is they have the slope going in the wrong way. So just want to make sure that everything is aligned, everything makes sense. Let's do part B. If we know that y minus y1 is equal to m times x minus x1, what's different about this problem? Well, this problem is not written in the traditional point-slope form. It looks like something's missing. If I rewrote this, I could rewrite this as y plus 5 is equal to -1/4 x plus 0. And this would be true, right? X plus 0 is the same thing as x. If I distribute -1/4 times x plus 0, I get -1/4 x. It's all the same thing. And we can figure out our point and our slope from our rewritten formula. It looks like our x1 is going to be 0, and our y1 is going to be -5, and our slope is going to be -1/4. So if we graph this, we're going to have a point at 0, -5, which is down here, 0, -5. And our slope is going to go down 1 over 1, 2, 3, 4. Down 1 over 1, 2, 3, 4. We can go ahead and draw a little line like this, where we have a negative slope because it's going downhill, and we're able to kind of just check to make sure everything makes sense. Cool. Let's go ahead and look at our next set of graphing questions, because in addition to like straight lines, we can graph a lot of different types of functions. The last lesson we had kind of a review of that fact. Today, we're going to focus on graphing quadratic functions. Quadratic functions are going to be any functions that have a highest degree of 2. So in this case, we have y is equal to x squared. The highest degree is 2. This is the parent function, which means it's the simplest, most basic form of the function. And if we wrote this in vertex form, which you guys should remember from like last year, we can say that we can introduce this concept of h and k, which help us find the vertex. Now, when graphed, quadratic functions, they form a U-shaped graph called a parabola. You can find its vertex, and if you know its vertex, you can apply the quadratic pattern. Now, one thing that I think helps students learn how to graph, because people are kind of iffy about graphing sometimes, one thing that helps graphing is, helps you when you graph is know that every family of function has a specific pattern. If you follow a pattern, you get a specific graph shape. And for quadratic functions, the same is true. That shape just creates a parabola. And if you change the x, then that's going to make a different shape. And when we're discussing the pattern, what we want to do is we want to think of like this little phrase that helps me think of these things. When you move over to the left or right or horizontally x units, it's going to move the next point up or down a times x squared. So like, it's kind of the hardest part of this lesson is to try to understand this. Like if you find the vertex, you have the vertex at any point, and we want to figure out the next point, where does this graph go? If you move over x units, then you're going to move up or down to find the next point at ax squared. Like, for example, let's say we have a vertex at, let's just say this point, and this function was f of x is equal to 2x squared. If I decided to move over x is equal to 1, I would move up 2 times 1 squared, which in this case would just be 2 units. And because parabolas are symmetrical, if I move in the opposite direction, like in this case, let's say x is equal to -1, the other point would be at 2 times -1 squared, which would end up creating a symmetrical parabola. All right, so all of this is very, I guess, theoretical until you start practicing the problem. What I want you to understand is that this function rule applies to every type of graph. If our parent function is x squared, then it's going to be a times x squared. But if you have cubic functions like x cubed, it would be move over x and you go up or down ax cubed. All right, you can just substitute that new function family in for that second part of the equation. All right, so we're going to practice this just a little bit. Hopefully this is going to make sense. And if you remember your Algebra 2, you're going to be able to find your h and k value based off of whether it's next to the x on the inside of the parenthesis or whether you're adding or subtracting at the end. So we're going to try to find our h and k. For this problem, if we know that y is equal to a times x minus h squared plus k, our h value is going to be -1 because it's the opposite sign. It's supposed to be minus h. In this case, it's plus h, so it's the opposite sign, so -1. And -4 because this thing moved down. Let's go ahead and graph this point. Our h and k is at -1, -1, 2, 3, 4, so somewhere around here. And if you want, you can label these points -4. Now, we want to go ahead and apply our pattern. And the truth is, when we talk about like, okay, what x do we want to plug into this formula? If we know that we have a vertex and we move over x and we move up or down ax squared, like you might be asking, well, what x do we pick? Well, you can pick any x that you want. The traditional numbers, you pick small numbers like 1 or 2 to try to plug into our value. On example B on this slide, we're kind of going to point out like, okay, when can we be more strategic about what numbers to pick? But generally, you can pick any number that you want. Usually keep the numbers small. So in this case, if I decided to say that x is equal to 1, because I'm going to go over 1 in the x direction, and I'm going to have to go up a times 1 squared. In this case, a is equal to 2. So this will be 2 times 1 squared, which is going to be 2 units up. So for this parabola, if I move over 1 in the x direction, I'm going to have to go up 2 units. Up 2 units. All right, now I can change my x value. If I change my x value to x is equal to 2, how many units will I go up? It'll be 2 times 2 squared, which is going to be 8. If I go over 2, I'm going to have to go up 1, 2, 3, 4, 5, 6, 7, 8 points. And you can see that it's going to grow pretty fast. One thing that we do note about all parabolas is that they are symmetrical, which means they are the same on both the right and left side of our vertex. So that means that we can simply reflect these points on our graph, and we'd be able to finalize our graph just by making a smooth curve through these points. So this would be an example of a parabola graphed using what's called vertex form. Just to recap, if you can find the vertex and you know the pattern, you can graph any function. Let's try this next one. Let's erase some of this stuff. And let's find the h and k for this function. Now I did change it a little bit just to kind of keep you on your toes. We have to find the h and k value for this function. If we said that f of x or y is equal to a times x plus h squared, or x minus actually, x minus h squared plus k, what would our h value be? Well, notice this problem is a little bit different. It doesn't have x inside the parenthesis. That means it's not going to shift over left or right. That means the h value is going to be 0. Our k value is just going to line up, same sign and everything, so it's going to be positive 3. And this parabola is going to start at 0, 3. Now, if you're wondering what is the a value in this case is 1/2. And if it helps you, we can think of the negative sign as a reflection across the x-axis, right? Or you can put the negative sign here. We know that if we start at a vertex and we move over x, we're going to go up or down a x squared. In this case, because a value is negative, it's going to open downward. It's going to be a downward-facing parabola, so we can expect this function to go downwards. When we plug in our values, what value should we pick? Well, I said over here on this example that you can always pick small numbers like 1 or 2 to kind of make your life a little bit easier. For this function, because we have a fraction of 1/2 and a denominator of 2, it's probably going to be better to pick a number that's even, like 2 and 4 when we plug these in, because we're going to have to multiply by 1/2, which is going to give us a number that's going to have to be divided by 2. So I'm going to go ahead and suggest that we're going to pick a number like 2 just to start. You could pick 1, but then you're going to end up with a fraction point. And when you're graphing, that's not a big deal, but it might make our life a little bit easier to graph with 2. That means when we plug in our function, we're going to have negative 1/2 2 squared, which is the same thing as negative 1/2 times 4, which is going to be negative 2. So this is telling us that when we go over 2 units in our x direction, we're going to go down 2 units to get our next point. Our graphs should have a couple of points on either side of the vertex. So the next point I'm going to pick is if x is equal to 4, we're going to go down negative 1/2 times 4 squared. 4 times 4 is 16, and 16 times negative 1/2 is negative 8. So if I go over 1, 2, 3, 4 units, I'm going to have to go down 1, 2, 3, 4, 5, 6, 7, 8 units. And one thing, keep in mind with parabolas always, is that they are symmetrical. So that means we can simply just reflect a couple of points on either side of our vertex. And when we connect our dots with the smooth curve, we end up getting a parabola that looks something like this. All right, so just to recap, if you can find the vertex using vertex form, you know where to start your graph. And the pattern for parabolas is always going to go over x units horizontally, is going to move you up or down vertically a times x squared. You'll see this on the homework. If you can pick one point on either side, it's going to give you a smooth curve. Cool. All right, now we're getting to like the fun stuff. All right, if you had fun with those last examples, you're going to really have fun here. All right, we're just going to review a little bit of factoring. We've talked about GCF factoring before. We talked about product sum factoring. We talked about factoring by grouping. One thing that we're going to introduce is the idea of factoring special cases. Now, there are two main special cases that you learn factoring through your time in algebra. Mr. Lopez's favorite one is called difference of squares. Difference of squares occurs whenever you have a perfect square minus another perfect square, and that can be factored into what are called conjugate pairs. Difference of squares makes conjugate pairs. For example, if I had something like d squared minus 81, what I could do is I could note that both d squared and 81 squared, or 81, are perfect squares, which means that if I figure this out, if I take the square root of d squared, I just get d, and if I take the square root of 81, I get 9. That's going to split this up into two different parentheses, where I get d plus 9 and d minus 9. Now, conjugate pairs, by definition, they look very, very similar. The main difference is one is a plus sign and one's a minus sign. So whenever we get this particular form where we have a perfect square minus a perfect square, it'll always break up into this other form called conjugate pairs. I like these problems because they're pretty easily identifiable. When we do a little recap right now, we're just going to keep any kind of factoring methods in mind. So let's look at example A. Looking at example A, 3x plus 9, this looks like it's an example of GCF factoring because both 3x and 9 can both be divided by one term. 3x and 9 can both be divided by 3. So when I factor out the GCF, the 3 goes in front, and left over after we divide is x plus 3. And this would be our fully factored form because x plus 3 inside the parenthesis can't go any lower. Okay, let's look at this next one. This next one, we're going to go ahead and note that this is an example of product sum factoring, where we're looking for the product of negative 28 that sums to 3. So product sum, product of negative 28, and sums to 3. Can you give me two numbers that multiply to make negative 28 and pause to 3? Yes. I know you had it in your mind, so like it was 7 and -4. I'm sure that's what you're thinking about. 7 times -4 gives us -28, and 7 plus -4 gives us +3. So when we factor these out into two binomials, we'll get n plus 7 times n minus 4. And because neither of these two terms can factor any lower, that would be our fully factored form. Now this next example, something a little bit more recent to what we just learned. This is an example of our difference of squares. Because both x squared and 16 can both they both have perfect squares. They both can be square rooted evenly. Also, it's a difference of squares because they always have to have a minus sign in between them. So if I take the square root of each term, I'm going to figure out that this is going to factor out to x plus 4 and x minus 4, because the square root of x squared is x and the square root of 16 is 4, and conjugate pairs by definition they have plus and minus in between them. Okay, last one on this slide. And if I had a note, I'm just going to note that this was an example of difference of squares. All right, last example, looking at this. It looked kind of like a difference of squares, but 2m cubed is not a perfect square, so that doesn't really apply just yet. It's not a product sum because there's only two terms. I'm going to go ahead and suggest the first thing we should always do is look for a GCF. Is there a GCF between both of these two terms? Yeah. They can both divide by 2m. So 2m factors in front. Left over, we have m squared minus 9. The instructions say factor each completely, and looking at the inside of this parenthesis, I can see that this can factor even further, because m squared minus 9 is also a difference of squares. So I would end up with 2m times m plus 3, m minus 3. And this would be our fully factored form. Just making sure that we can factor as low as we can go. Last slide, just a little bit of review of exponent rules because we just took a test and this was asked as kind of an extra credit question, and so many people skipped this question that and didn't even attempt it that I felt like we probably should review some exponent rules. Now, here are a couple of exponent rules that we can kind of go over. The first one is when you have like bases and you multiply them together, you're going to add the exponents. So in this case, x squared times x cubed is x to the power of 2 plus 3, which is x to the power of 5. If you divide like bases, it's like subtracting the exponents. So in this case, 2 minus 3 is -1. If you have a power raised to a power, an exponent raised to another exponent, you can multiply these values. You can multiply these two together, and you get x to the power of 10. And one last thing, whenever you have a negative exponent, in our previous lesson, we'd want to make all of these negative exponents positive. And the way you do that is by moving it to the other side of the fraction bar. In this case, 1 over x to the power of -2 can become positive. If you move that x to the power of -2 to the numerator, it becomes x squared. So what's negative in the denominator is positive in the numerator, and also vice versa. Today, we're going to do just a little bit more of that, those exponent rules, but we're going to practice bringing every variable to the numerator, because oftentimes in a calculus class, this might be a strategy that you'll have to utilize. So we're going to simplify each of these expressions using the rules that we already know, But in this case, if you ever have a variable in the denominator because the instructions ask you to, we're going to bring them to the numerator. We're just going to practice doing that real quickly. So one thing that I find helpful when I'm separating these problems is I can go ahead and say this is the same thing as 9 over 3 times x squared over x times y to the 5th over y to the 7th. I kind of separated them, numbers with numbers and like variables with each other, so that when I simplify these one at a time, I can figure out what do we have left over. 9 over 3 reduces to 3. If I have x squared divided by x, that's the same thing as subtracting the exponents, and I have 2 minus 1, which is going to be 1. So I have just x to the power of 1, or x. And lastly, I would end up with y to the 5th divided by y to the 7th. And if I subtract them, I'm going to end up with y to the power of negative 2. Now, this would be our answer in this case, because in our previous lesson, we tried to make any negative exponent positive, which is a good skill to practice, but today we're bringing everything in the numerator, so we leave our answer just like this, because everything is in the numerator. Okay, last example in the video. We're going to simplify this one further, because there's a couple of rules that we have to follow. All right, if I simplify the top here, I have x cubed. But I have a power raised to the power for our base of y. So this becomes y to the power of 9, because you would multiply a power raised to a power. This is going to be over. In this case, we have x to the first power and y to the first power. And these are also raised to the powers. So this would be x to the power of negative 2 and y to the power of negative 2. Now I can simplify these by splitting these up even further, just to kind of help us visualize what's going to divide with what. I have x cubed divided by x to the negative second power times y to the 9th over y to the negative second power. You do not have to split them up like this. I just think this is helpful for us to kind of see what goes with what. We're going to use our division rule that says this is the same thing as x to the power of 3 minus negative 2 times y to the power of 9 minus negative 2. And if we simplify these even further, 3 minus negative 2 is the same thing as 3 plus 2, so x to the 5th. And y to the power of 9 minus negative 2 is the same thing as 9 plus 2, which is y to the 11th power. I note that both of these are in the numerator. There is no denominator, so by definition, they're still in the numerator. And we have our answer. All right, well, that was fun. I would encourage you guys to watch this video as many times as you want. Make sure to like and subscribe. Make sure you guys, give me all the follows that I can get as I post this on YouTube. Hopefully this made sense, and if you have any questions, you can definitely ask. This homework assignment is going to be due later because we have the experiential education trip coming up. So take your time with it, not too much time. Let it soak in, and hopefully this all made sense. All right, see you next time. Bye.